The goal of this lecture is to go over the basic principles of EKG. So here are my objectives. My objectives are that you would understand what the EKG provides, and that you'll be able to recognize that depolarization of cardiac cells proceeds in an orderly fashion in a normal situation, starting at the sinus node and moving to all the way to the ventricles. And that you will recognize that the electrical activity of the heart is captured by recording electrodes or leads placed on both arms and legs. So if you're going to remember anything from this lecture, I mean, this is the bottom line, kind of the take-home messages for me, that the EKG provides a graphic record of the electrical activity of the heart, that depolarization of the cardiac cells proceeds in a orderly fashion, starting from the atria to the AV node and to the ventricles, and that the sequential movement of electrical current with each depolarization from the sinus node to the entire ventricular myocardium creates specific phases of the EKG, which we will go over. And then the electrical activity of the heart is captured by recording electrodes or leads placed on both the arms and the legs, called the limb leads, and then 6 on the chest called the precordial leads. Okay, what's an EKG? Let's start with Dr. Dejani. How would you define an EKG?
It is an electrical activity. It is a presentation of the electrical activity of the heart.
Presentation of electrical activity of the heart. Good, excellent. So, good. So EKG is a representation of electrical activity of the heart, as you said. 3 things. We're talking about the heart, we're talking about electrical activity, and we're talking about graphic representation. Okay? All right. Who can tell me what's number 1? If you watch the video, this should be an easy answer.
It is SA node.
SA node. Okay. Number 2. Okay. Dr. Makbib, I didn't hear you, but I think you said internodal pathway. Number 3.
It is AV node.
AV node. Number 4, bundle of His. So I'll just tell you what number 5 and number 6 are. So number 5 is the left and the right bundle branches. And then number 6 is the Purkinje fibers. Okay, so this is the electrical activity of the heart. Who can tell me, this is an important aspect. So who can tell me the difference between the picture that we're seeing on the left and the picture we're seeing on the right? Someone from Bahardar.
So the first picture is the action potential picture of the muscular system, mainly the ventricular muscular action potential, which has 4 phases of action potential or depolarization, whereas the second picture shows action potential or depolarization of the normally the pacemakers, mainly SA node and AV nodes, and they usually miss stage 3 and 2. No, I mean 1 and 2.
They don't have stage 1 and 2, you're correct. What is another important difference between the 2? And I'm giving you a hint by moving my mouse. Can you tell me why number 4 looks different and what the significance of that is?
Normally the stage 4 there's a difference in resting membrane potential. On ventricular system, there is a low resting membrane potential, whereas pacemaker cells have higher or less. This helps us pacemaker cells to,
Okay, I think you said it right. Your voice not heard very well because of the internet connection, but I think what you said is absolutely correct. So the big difference between the ventricular action potential and the nodal action potentials is in stage 4, in the ventricular action potential, you require a stimulus for you to have an action potential, as opposed to for the pacemaker cells, the stage 4 is not stable. You still have influxes of calcium and potassium to where it will automatically generate an action potential without the need for an external stimulus. So this is a very important difference between the two different cells. And it is this property that allows the SA node and the AV node to be the pacemakers of the cells. And it's when they contract, the rest of the ventricular muscle cells follow and they contract. So that allows them to be the pacemakers of the heart. I hope that's clear. Thank you so much. All right, so as we mentioned earlier, the SA node will have its action potential. And for each of the different tissues we talked about, they have their own action potentials. So the atrial muscle will have its action potential. The AV node will have its action potential, then followed by the common bundle of His, going through the bundle branches, going through the Purkinje fibers and the ventricular muscles. So what happens is for one cardiac cycle, when you add up all these action potentials, you will get what we know as the PQRST. And that's how it's represented on the EKG. Okay, so hopefully that was clear from the lecture. So we're going to talk about lead placements. So if we are talking about the 3 limb lead systems, what are the names of those 3? Someone from BDU, tell me what the names of these 3 leads are if we're talking about the limb lead system.
Lead 1, lead 2, and lead 3.
Okay, good. I heard lead 1, lead 2, lead 3. Excellent. And you can look at the directions of those leads. Okay, augmented limb leads. Someone from Haramaya?
Those are AVL, AVR, and AVF.
Good. AVR on the right hand, AVL on the left hand, AVF on the foot. Excellent. And then to that, we add what we call the precordial leads, and this is how they are put: 1, 2, 3, 4, 5, 6. And the combination of those is what gives us our 12 lead EKG. Okay. So before we look at what a normal lead EKG is, I think this is an important concept that we need to cover. So all EKG does is it has a negative and a positive lead, and it measures the electrical activity in that vector and gives you a signal on a paper. Okay. So for example, if I have cells here, if the cells depolarize from here to the right, if I put my lead from here to here, I'm going to get a positive deflection. So lead A, if negative is here and positive here, the electrical activity is going that way, it will interpret it as a positive deflection. Now, what happens if I switch the negative and the positive? For the same electrical activity, I'm going to get a negative deflection. Okay. What happens if I put my leads perpendicular to where the electrical activity is, which is how lead C is placed? Then I'm not going to pick up any electrical activity on that paper. So this is how EKG works. There is the electrical activity in the heart, and then we place the leads on different directions, and the same electrical activity is interpreted differently based on where the lead is placed. So when we put all of them together, you can see that, you know, our heart is placed here, and we'll be able to pick up electrical activity in all these different directions, which gives us this 12 lead EKG reading. So we have lead 1, lead 2, lead 3. We have AVR, AVL, AVF, and then the precordial leads, we have V1 through V6. Okay. So really, EKG is all about pattern recognition. And once we learn what a normal EKG looks like, when there's something abnormal comes, we'll be able to pick it up. So typically in lead 1, you'll see a positive deflection of the QRS. The same with lead 2. In lead 3, it's a little bit smaller. AVR in a normal person, usually the QRS is flipped. AVL, you'll have a small positive deflection, the same with AVF. And then when you march from V1 through V6, you go from negative deflection, slowly moving to positive deflection of your QRS. So you look at this and you recognize this pattern. And once something looks different than that, you'll be able to pick up abnormal findings. Hopefully, if you watch the video, all I'm doing right now is review. Okay, so then again, on a normal person, the intervals between the different signals that we see, the P, the QRS, and the T, there's normal amount and there's abnormal amount. So it's important for you to know what the length of each of these are. So who can tell me what is considered a normal PR interval? How many seconds or how many boxes on an EKG paper tracing would be considered a normal PR interval?
It is around 3 small square.
3 small boxes.
It ranges to 0. The normal timing for PR interval will be ranging from 0.12 to 0.2 seconds.
Good. Good. So, and that would be, anywhere from 3 small boxes to 5 small boxes, right? Or 1 large box. Good. What's a normal QRS interval?
From 0.06 to 0.1 seconds.
Good. So it should not be no more than 3 small boxes, right? Okay. So here are the values. So P wave by itself should not be more than 3 small boxes. The PR interval should be between 3 and 5 small boxes, or no more than 1 large box. QRS should not be more than 0.12 seconds or 3 small boxes. And then the QT interval should be in a male should be less than 0.44 seconds. And that takes into consideration of your heart rate. Okay. So if you see QRSs that are longer than this, then there's some abnormality with the electrical activity in the heart. If the PR interval is longer than that, then there's some abnormality in that EKG. And that's knowing normal is what helps us identify what's abnormal. Okay. We're going to cover like a step-by-step ECG evaluation that's going to help us identify some common EKG pathologic findings. And really my goal is not that you will be experts on knowing what the diagnoses are, but being able to identify what is abnormal about that EKG tracing compared to what we've covered as normal. Okay, so even though we're going to look at some pathology, really my focus is going to be for you to tell me, okay, when I look at this EKG, I see this feature that would abnormal than what we have covered, is how we're going to go over by it. Okay. So when I look at an EKG, I try to think about 4 steps. First thing is I want to locate the P wave, make sure that I have a P wave and look at the characteristics of the P wave. Then I look at the relationship between the P waves and the QRS complex. After that, I will look at and analyze the QRS morphology, followed by focusing on the ST segments and the T wave. And I kind of force myself to go through all these 4 steps so I won't miss anything, okay? So locate where the P wave is, establish the relationship between the P waves and the QRS complex, analyze the QRS morphology, and then focus on the ST segment and the T waves, okay? All right, so we're gonna look at some EKG strips, and as we look at those EKG strips, and as we identify what's abnormal about them, we will also discover their diagnoses, okay? All right, so I'm not necessarily interested in you telling me what the diagnosis is, but I want somebody to describe to me what do you see abnormal in this EKG?
Regular rhythm and the P wave is not visible.
So I heard the rhythm is not regular, and I heard the P wave is not visible. Okay, I guess, so I agree with you.
Yes.
Okay, so the QRS is irregular. It's not coming at an appropriate time.
Yes.
And then you also don't have clear P waves before the QRS. You just have squiggly lines kind of all over. Okay, so that's the abnormality that we see. When you see that, that diagnosis is called atrial fibrillation. So when I think of the P wave, these are the questions that I ask. Is there a P wave visible or not? What is the rate of the P waves? But we just answered we just don't have any P waves. If you don't have P waves, then that diagnosis is atrial fibrillation. And that EKG was an example of atrial fibrillation. Okay? Here are some more examples of atrial fibrillation. You don't have really clear P waves, you just see squiggly lines. And because the signal that you get from the atrium is irregular, then the ventricle, some of the electrical activity gets passed to the ventricle, and then the ventricle beats in an irregular fashion. So that's a classic finding of atrial fibrillation. Okay, another question. So it says, from what to what did this rhythm change? So again, not interested in the name, but I want you to tell me what abnormality you see here, and then what abnormality, if any, if you see on the second part of the EKG.
There is seesaw appearance in between the QRS complex.
I don't know what you mean by seesaw. Can you describe seesaw to me?
As I think between the QRS complex, there is some rhythm irregularity that.
So you are seeing, you don't see a P wave followed by a QRS all the time.
Yes.
Right? But you see multiple P's and then you have a QRS, multiple P's and a QRS. Is that what you mean by seesaw?
Yes.
Okay. All right, so that's the first half. How about the second half of the image?
The T wave is maybe flat or it is not well visible.
That there's a T wave right there. You guys can see my mouse, right?
Yes.
Okay. So to me, the second half of the EKG is normal. You have P wave, QRS, T. You have P wave, QRS, T. P wave, QRS, T. So I would say this part is normal, but this part, as you said, you have a lot of P waves before you have a QRS, a lot of P waves before you have QRS. So when you recognize that abnormality, that's called atrial flutter. When you have P waves that are over 260 times a minute, then that is classic for atrial flutter. And here are a couple more examples. So the atrium beats in a really, really fast manner, and then you'll have QRSs every maybe third or every fourth beat. And that's what we call atrial flutter. Good? Okay. What abnormality do you see here?
I'm seeing a sinus bradycardia.
Sinus bradycardia. Okay, you're telling me the diagnosis, but I want you to describe to me what is abnormal about sinus bradycardia, or how do you describe it in EKG forms? Because we're just looking at electrical activity and comparing from normal. Your diagnosis is correct.
There is Q is present, but the RR interval is prolonged more than 8 segments, large boxes.
Good, good. So
the RR interval is prolonged.
Good. The RR interval. So between this R and R, you have a ton of boxes. So we're going to talk about how we identify if the rate is less than 60, we call that bradycardia. The P waves between one P wave and another P wave, if that rate is less than 60, we call it bradycardia. And that's exactly what we saw here. Okay, so how do we determine a rate? We determine a rate by looking at, you can do the RR interval, and you do 300 divided by the number of large boxes between two waves. So for the first one, we have 1, 2, 3, 4, 5, 6, 7, almost 8. So 300 divided by 8 gives us about 37. So the top person has a heart rate of 37. Okay, this next guy has a heart rate of 1, 2, 2.5. So 300 divided, that's about 120, I think. Yeah, this person has a heart rate of 120. And this person has 1, 2, 3, 4. So 75. Is that clear? That's how we determine heart rate. Once we know that it's sinus. And what's the definition of a sinus rhythm? A sinus rhythm is defined by each P wave is followed by a QRS. Okay.
How to determine if the rhythm is irregular? How to determine the heart rate if the rhythm is irregular?
Good question. So how do you determine the heart rate if it is irregular? If it's irregular, then you get a long strip of EKG tracing, and you count how many QRSs you have, and then you know the time for each of those boxes. So for the number of boxes that you have, you count how many, let's say, you take a full strip of a 10-second strip. So within 10 seconds, if you have 8 QRSs, then you multiply 8 times 6. Then that's how you determine the heart rate. You can only use this formula if you have a regular rhythm. Otherwise, you have to do it kind of manually.
Another question. There are cases to calculate the rate for rate determination. They are using 1,500 divided by the number of small boxes. Is that okay?
If you want to make your life difficult, sure. You can, because I mean, the way you're doing it is, we're using 300 by large boxes, but in each large box, there are 5 small boxes. So 5 times 300 would be 1,500. So you can do 1,500 divided by the number of little small boxes. So If you do that here, it would be 5, 10, 12. You'll end up at the same place, but you can't do that. Yes. Okay, let's keep going then. Okay, so you don't necessarily have to tell me what type of heart block this is, but you can describe to me what you see.
Again, there is a rhythm irregularity.
Aman, I want the students to participate, not you. The residents, and it's okay to be wrong.
There is absent QRS complex.
Correct. So for example, this one, this P wave does not have a QRS complex. You're right. That's correct. And again, this P wave does not have a QRS. What else do you see?
The other is P wave is inverted.
Okay. On one of the beats, it looks like the T wave is inverted. Sure. Okay. What else? There is another more obvious thing that I see. So I want you to look at the PR interval, okay? So look at the PR interval here. It's pretty short, right? And then look at the PR interval here. It's longer. Then it goes back to short PR interval, long PR interval, short PR interval, long PR interval. Okay. So this is a classic heart block where the PR interval continues to get longer and longer until you end up dropping a beat, meaning not having a QRS. And then the cycle starts again. Okay. But you don't have to know the diagnosis. All you have to recognize is, okay, in a normal sinus rhythm, the PR interval is fixed or it's the same. But on this one, the PR interval is changing. So that's the abnormality I want your eyes to be able to start picking up, okay? So that is where we're gonna talk about establishing a relationship between the P wave and the QRS complex, okay? So what are the questions that I ask when I look at an EKG? I ask, are the P waves associated with a QRS complex in a one-to-one fashion? If they're not, are there more P waves or QRSs? And I ask, what's the atrial rate and what's the QRS rate? And then I also ask, what's the PR interval? Is it fixed or does it change? When you try to answer these questions, you'll be able to identify some diagnoses. Okay, so this is a great slide on heart blocks. Okay, so there are 4 different kinds of heart blocks. Okay. The first one is called first degree heart block. All first degree heart block is just prolonged PR interval. Remember we said a PR interval should not be no more than 1 large box or 0.2 seconds. So whenever the PR interval is longer than 1 large box, but it's the same, it's fixed, it's consistent, that's called first degree heart block. Okay. Then we have Mobitz type 1 or second degree heart block. This is an abnormality where you'll have progressively increasing PR interval until the QRS wave is lost. And that was the example of what I showed you earlier. So the PR interval goes narrow, bigger, bigger, until a point where you drop a QRS. Then the cycle starts again. When you have that, that's called Mobitz type 1 second degree heart block. Okay, then you have second degree heart block type 2. Type 2 second degree heart block is your PR interval is constant, but you just drop random QRSs. So maybe every second beat or every third beat or every fourth beat, you drop a QRS. When you have that, that's called second degree heart block. Then last is the third degree heart block. Third degree heart block is you lose the communication between the atrium and the ventricle. So the atria contracts on its own, and then the ventricle contracts on its own. Typically, the ventricular speed is much slower than the atrial speed, but there is no communication between those two. When that happens, we call that third degree heart block. Okay. All right, so let's look at some examples. The top one, what do you think is happening on the top one?
It seems type 1 heart block.
He said type 1,
Yeah.
second degree type 1, right? Good, yeah, so short PR interval gets longer, gets really long, then you drop, you have a P by itself, and then you start the cycle again. Short PR increases, and you drop a QRS. Good, how about the second one?
Type 1 moves to.
Type 1
Type 2 moves.
It's second degree and Mobis type 2.
Mobitz type 2 second degree heart block. You are correct. So the PR interval is fixed. It's not changed, right? But all of a sudden, a P is by itself. There's no QRS. So it looks like every fourth beat, you miss a QRS. So that's a second degree heart block. Good. And then how about this one, the third one?
Third degree heart block.
Okay. Does everyone agree? Should get a hint from the way I'm asking the question. Okay, so you said third degree heart block. One of the criteria for third degree heart block is the atrium and the ventricle don't talk to each other. They do their own thing, right? So if this was a third degree heart block, why would we have a fixed PR interval? If you see all the QRSs you see, they are preceded by a P wave, right? So if this was a third degree heart block, they shouldn't be like, there should not be a fixed PR interval. Like the P shouldn't be talking to the QRS. Okay, so this one is a really, really bad second degree heart block type 2, meaning it's only every 1, 2, third. It's every third P wave that gets a QRS. Here's an example of what a third degree heart block looks like. So you can see we have put arrows where there's P waves. So the P's are marching in their own time. And then the ventricle is marching in its own time. And you can see that the ventricular rate is constant on its own, meaning from this QRS to this QRS, it's the same amount of length between the QRSs. And the length between each of the P's is the same. So the atrium is doing its own thing in a regular rate. The ventricle is doing its own thing in its own rate, but slower, but they're not talking to each other.